Now, in our motion unit, we looked at the difference between distance and displacement, and we saw that they're similar, except displacement is known as a vector quantity because it includes direction, whereas distance doesn't, and so it's known as a scalar quantity. Now, we've just been looking at vectors, and so it seems pretty obvious then that they involve a distance and a direction. That's why we're calling them vectors. But what happens when we multiply them by a scalar quantity? A scalar quantity could just be a number, a constant. Now, for all vectors, A, and scalars, let's call them delta and mu, but all we really mean by delta and mu is that these are just numbers or some sort of scalar quantity. What happens if we multiply them? Well, there's these set of rules here. Let's have a look at what each one of these means. If we take some vector and we multiply it by 0, we get the 0 vector. So we write that really just with a 0 with that squiggle underneath to show that it is a vector. And that's shown as just a dot. Okay, it doesn't actually go anywhere and it has no direction and no distance. If we multiply a vector by 1, then we just get that vector. That makes sense. And if we multiply a vector by -1, we get negative vector, and we've seen that that runs the vector in the opposite direction. But what if we multiply a vector by some number? If we had, say, 4 times a certain vector, what would that do? Well, it's going to change the length of the vector, but not the direction. So if we had, for example, some vector A that looked like this, and then we had a look at another one that was, say, 4A. 4A is just going to be 4 times as long and go in exactly the same direction. I'll just put the vector under the A there. So we can see that it changes the length of A, but the new vector is still going to be parallel with the old one. The direction hasn't changed, just the length, and that seems pretty obvious. So it could be that the scalar quantity that we're multiplying by might be positive, like 4, or it could be negative, and we've seen what happens when we multiply by -1. Now, clearly, if you're multiplying something by -4, you could multiply it by 4 and then multiply it by -1. So it seems fairly clear that you could combine these two rules to say the absolute value of the thing you're multiplying the vector by and the absolute value of the vector will give you the absolute value of the two things multiplied together. That's fairly straightforward. And this bottom rule here, which is really just combining the fact that we could be multiplying two scalars together, says that if you've multiplied a vector by a scalar quantity, then we can see what that's going to do. If you then multiply that by another scalar quantity, what you'll get is just the two scalar quantities multiplied together, multiplied by the vector. Now, this looks very confusing with all of these Greek symbols, but really to make a simpler example here, if we were going to say that we had 2 multiplied by 4 lots of a vector, say, then we've already seen what 4 lots of that vector looks like. If we're then going to double it, then it will then be twice as long, and what we'll end up with is 8 lots of the vector. Same direction, 8 times as long. So most of those rules are fairly straightforward. And 2 more rules to look at, both of them looking at the distributive law. Here we've got a multi-term vector multiplied by a single scalar quantity, and we can see that it does follow the distributive law as we might expect. Now, all the vectors here, both of them, and there might be more than 2, are going to change in size with the same proportion. So that's going to make a shape that is mathematically similar, not just a little bit similar, but mathematically similar. So the rules for similar triangles or similar shapes all apply. There's going to be equal angles everywhere. Things will be parallel in each shape, and we'll have those scale factors that can go from one to the other. So example here, we've got vector A and vector B. That gives us vector A plus B. But if we'd multiplied and said we want, say, 2 lots of vector A plus B, then we can see that that means we've got 2 vector A's, which is just a section here that's twice as long, same direction, and B will be turning into 2B by just being twice as long. And so, of course, this length here will also be twice as long. And we'll end up with a triangle that is exactly twice the length. All of the lengths will be twice of what they were, and it'll be similar. Now, down here, we've got a multi-term scalar multiplied by a single vector, and it follows the distributive law as you would expect too. And this is similar to what we looked at before when we were multiplying, except that we'd be saying, all right, let's put some numbers in here. If we had 2 plus 3 multiplied by some vector, it's like saying we've got 2 lots of the vector plus 3 lots of the vector. 2 lots of the vector would make it twice as long, and 3 lots of the vector would make it 3 times as long. So if we add those together, we're going to have a section that's twice as long, another section that's 3 times as long. We're going to end up with 5 lots of the vector, which makes complete sense.